Hey everyone, and welcome. Ever wonder how Netflix just knows what movie you'll want to watch next? Or how a store can figure out who its most valuable customers are? Well, the secret is usually buried in data. And today, we're going to pull back the curtain and show you how to find those hidden patterns using a really cool technique called data clustering. So, let's get into it.
Here is what we're going to cover. We'll kick things off with the basics. What is data clustering? Then, we'll open up the toolkit and look at the most common algorithms. After that, we'll talk about how you actually choose the right tool for your data. We'll also solve that nagging question. Just how many clusters should you be looking for? And finally, we'll wrap it all up with the key takeaways you can start using right away.
All right, let's jump right in. First up, what exactly is data clustering? At its heart, it's really just about finding the natural, hidden groupings that already exist in your data. Let's try an analogy. Imagine you have 1,000 photos just sitting on your computer. No folders, no tags, nothing. How would you even start to make sense of them? Well, you'd probably just start making piles, right? You put all the beach vacation photos over here and all the city pictures over there. That instinct you have to group similar things together, that's exactly what clustering algorithms are designed to do, just on a massive scale. So here's the more official definition. Clustering is what we call an unsupervised machine learning technique. Now that word, unsupervised, is the real magic here. All it means is that we don't give the computer any hints or answers ahead of time. We don't say, these are the groups. We just hand over a big, messy pile of data and tell the algorithm, okay, you figure it out. It has to find the patterns all by itself. Now, to really get this, there are just 3 quick terms you gotta know. First, a cluster. Well, that's just one of the groups the algorithm finds. Simple. Second, the centroid. Think of this as the dead center, the heart of each cluster. And third, distance metrics. That's just a fancy way of saying the ruler. It's how the algorithm measures how similar or close any 2 points are to each other.
Okay, now that we're all speaking the same language, let's open up the Data Scientist Toolkit and check out the most popular algorithms you're going to run into.
First up, we've got the rock star of clustering, K-means. This is probably the most famous one, and for good reason. It's fast, it's efficient, and it's pretty straightforward. Its whole job is to take all your data and slice it into a number of groups that you specify. We call that number K. So if you're a retailer, you might say, I want to find 3 groups of customers. K-means' mission is to find the best possible 3 groups it can.
So how does it actually pull this off? It's a pretty clever little dance, actually. First, it just randomly drops K centroids onto your data. Then it starts a 2-step process. Step 1, it assigns every single data point to whichever centroid it's closest to. Step 2, it finds the new center of each of those fresh groups and moves the centroid there. And it just repeats that dance, assign, move, over and over again until the groups stop changing and everything settles down. Now, nothing's perfect, right? The big pro for K-means is that it's an absolute beast with large datasets. It's so fast and it scales really well. But it has one huge catch. You have to tell it how many clusters to look for. You have to give it that K value. Picking the right K is a massive challenge, but don't worry, we're going to come back to exactly how you solve that problem a little later. Okay, next tool in the box, hierarchical clustering. This one is completely different. Instead of just giving you a single final answer, it builds this beautiful family tree of your data. This is super useful because you can see how different groups are related at various levels. Biologists love this for building the tree of life. It can work from the bottom up, starting with every point as its own cluster and then merging them, or top down, starting with one giant cluster and breaking it apart. And this brings up a really important question. When the algorithm is trying to decide whether to merge 2 big clusters, how does it define distance? Does it look at the 2 closest members in each group? That's called single linkage. Or does it look at the 2 members that are farthest apart? That's complete linkage. It sounds like a small detail, but trust me, this choice can totally change the entire structure of that family tree. Our third and final tool is called DBSCAN, and this one is a specialist. It thinks about the problem in a totally different way. It doesn't care about centers, it cares about crowds and density. It looks for dense neighborhoods of data points and calls those clusters. And what about the lonely points, the ones off by themselves? DBSCAN is brilliant. It just labels them as noise or outliers and moves on. This makes it perfect for finding weirdly shaped clusters and for dealing with messy real-world data. So DBSCN's superpower is its ability to find clusters of pretty much any shape you can imagine, and it's fantastic at automatically ignoring noise. The catch?
It's really sensitive to its two main settings. You have to tell it how close points need to be considered neighbors, that's a parameter called epsilon, and how many neighbors a point needs to have to start a crowd, that's min PTS. If you can get those two settings right, it works like an absolute charm.
Okay, so we've got 3 great tools, but how do you know which one to pick? This is where the real skill comes in, matching the right algorithm to your data.
Let's think of this table as your go-to cheat sheet. If you've got a ton of data and you suspect your clusters are probably kind of browned and blob-like, k-means is your best friend. If you're more interested in the relationships between clusters and you're not sure how many there are, try hierarchical. But if your data is a mess, full of noise, and the clusters could be any weird shape imaginable, that is a job for DBSCAN for sure.
All right, let's circle back to that big problem with k-means we talked about. We have to tell it k, the number of clusters, but seriously, how on earth are you supposed to know that number ahead of time?
This isn't a small thing, it's one of the most critical decisions you'll make. If you pick a k that's too small, you're lumping distinct groups together. If you pick one that's too big, you're splitting natural groups into meaningless little pieces. It's a real Goldilocks problem. So, how do we find the one that's just right?
Well, one of the most popular ways is called the elbow method, mostly because it's so visual. Here's the idea. You run k-means a bunch of times, trying out a range of k's, like from 1 to 10. For each run, you measure how tight the clusters are. Then you plot the results. You'll see that as you add more clusters, your score gets better, but at some point it starts to level off. You're looking for that point of diminishing returns, that sharp bend in the graph that looks just like an elbow. That's usually a great bet for your optimal k.
The second method is a bit more mathematical. It's called the silhouette score. Here, you also test a range of k values. But for each k, you calculate a score that basically asks, how well do these clusters fit? A high score means your clusters are dense and well separated from each other. So the logic is super simple. You just run your tests and pick the k that gives you the highest score.
So, which one do you use? Well, the pro move is to use them together, like a team. Start with the elbow method. It gives you a great visual, a ballpark estimate for where k should be. Then, once you have a smaller range of options, you use the more precise silhouette score to zoom in and make your final confident decision.
We have covered a ton of ground. So let's boil this all down to the most important things you need to remember from all of this.
Okay, here we go. Takeaway number 1. Clustering is your secret weapon for finding the hidden structure in your data when you don't have any labels to work with. Number 2. There's no single best algorithm. It's always about matching the tool, whether that's k-means, hierarchical, or DBSCAN, to the unique shape and size of your data. And number 3, and this is a big one, when you use k-means, don't just guess k. Use the elbow method and the silhouette score together to make a smart, informed choice.
So there you have it, a quick look at the world of data clustering. But I want to leave you with one final thought. Think about your daily life. The songs in your favorite playlist, the restaurants in your town, even the people you follow online. Now that you know the logic behind it, you'll probably start seeing potential clusters everywhere. The only question is, what hidden patterns are you going to spot first?